Hi, I'm Tim Gore, and today on the Science Behind series, we look at the science behind the new Mississippi River Bridge that has just opened in St. Louis, Missouri. This video animation gives you an idea of what the bridge was designed to look like. The bridge opened just last weekend to gala ceremonies, and we're going to be joined by a couple of engineers who worked on the bridge project today to answer your questions about what it's like to put a cable-stayed bridge together, how do the forces of physics work to make sure that a cable-stayed bridge stays up when you decide to drive across it, as you're seeing here in the animation. We'll be joined, as always, by interactive video conference schools across the country. To those of you watching via the web or television, don't forget that you can email us your questions to live@hectv.org. That's live@hectv.org at any time during the program. We look forward to your questions becoming a part of the program. This animation shares with you what the bridge was designed to look like. We've also got some video we can show you of the completed bridge, which was just taken last weekend. So here you see a nice pull-out shot of the tug going up the Mississippi River, and there you see an example of the completed bridge, a 1,500-foot span across the Mississippi River just north of the Arch in St. Louis, Missouri. We're looking forward to your questions throughout the program. Don't forget, email us at live@hectv.org. We're being joined now by a couple of engineers who worked on the project. I want to invite them into the discussion. Randy, thanks so very much for being here.
Thank you.
This is Randy Hitt. Randy, let everybody know what it is you got to do on the project.
I was the project director for the owner, which is the Missouri Department of Transportation. On behalf of Missouri and Illinois, we oversaw the design and construction of the project.
And to his left is Jeff Smith, who's also obviously important to the project. Jeff, what did you get to do?
Tim, I was project manager for the design firm, HNTB Corporation. We designed the bridge. We advised Randy and his crew during construction as to what the intent of the design was so that everything went together as well as it could and meet all the requirements.
So it's hand-in-glove operation.
Certainly.
To make sure that it works. Hopefully the hand fits into the glove and the glove fits on the hand very nicely. But as project manager, that means you guys are overseeing everything?
Yes, overseeing everything from the early stages, design, location, all through all the different design aspects, and procuring a contractor and overseeing all the construction, making sure the quality assurance, quality control, and importantly for the contractor, make sure they get paid on a timely manner as well.
Oh, well, Jeff might care about that. It opened just last weekend. Jeff, take us back in time. When did you all start this? How long has the process been?
Well, the planning process goes back nearly 20 years, but we got involved pretty heavily about 6 years ago. With the design process. We started laying out pier locations, working with the Corps of Engineers, MoDOT, and others to figure out the best way that we could design and build this bridge. So design took a little over a year itself, which was really an extremely aggressive schedule. Everything had to keep moving. All the pieces had to keep moving in the right direction at the same time, and it was great, working with everybody, and exchanging that information as we move forward. So that was about 2 years, year and a half for design, and then 4 years for construction, which we just wrapped up.
Well, it's great to see it finished. I get the pleasure of looking at it every day from my window, and it's just spectacular to see. Let's start talking about some elements of bridge design. Gentlemen, I'll invite you to join me up here at the table, because we want the world to understand some of the major concepts at work when we think about what engineers have to care about when they're developing and designing a bridge. So I'm going to take these couple of books, and we're going to assume for a moment that these books represent like bridge piers. And our lovely sponge here is going to represent the surface of the road. Now let's talk a little bit about the nature of what's called load and types of load, because obviously the bridge has to make sure it sustains all sorts of different types of load, correct?
Right.
There's a live load, there's dead load, there's dynamic load. Jeff, talk a little bit about that. What is load and how does that affect the design?
Okay. When engineers talk about loads, they're talking about the forces that are put on the bridge or any other component. Dead loads sounds kind of morbid, but those are the things that are always there, the concrete, the steel, things that are part of the structure itself. Live loads are things that are changing. People driving across it in trucks, wind, temperature forces as the bridge expands and contracts, earthquakes, things like that, forces from the river itself. So on a bridge like this, you've got a lot of different live loads to consider.
Okay, so all those live loads make a difference as you think about the kind of bridge you're going to design and where you're going to put it. And we want to talk about different kinds of bridges now to give you a sense of how they all operate with some of these important concepts that we'll discuss. First, we want to share some information about a beam bridge. We've got an image of the city of St. Louis where you see a number of different bridges on St. Louis. St. Louis, of course, is a city of bridges. We're right there along the Mississippi River. And that one you see kind of in the middle of the picture, the Poplar Street Bridge, is an example of a beam bridge. Let's talk about forces that are at work when we go to a beam bridge. Now, one of the terms I hear about is something called bending, Randy.
Yes.
What does bending mean?
Well, bending the forces there, and as you see in a girder, you know, it doesn't stay absolutely true. So it is going to have some forces and it's going to bend, and that's by design. You can't have something that's just perfectly like that. It wouldn't withstand the forces.
Okay, so if I look at my sponge here, which represents my deck surface, we don't want this to be rigid. We actually want it to have some give, correct?
Yes.
And that's important just to make sure it handles the elements that change in temperature and all that kind of stuff?
Correct. And the important thing, what we see, is to have something that counters forces. The main components of the bridge are concrete and steel. Concrete is very strong in compression. When you try to press it together, holds a tremendous amount of load. Concrete's not very strong in tension when you try to pull it apart. That's why you need the reinforcing steel in a bridge. The reinforcing steel takes up the forces of tension. So that's the reason you have to know where the areas of tension are and make sure that's where the reinforcing steel, and that's what our designers provide for us.
And you see there the definitions of both compression and tension as Randy refers to them. And in our little example here, we'll show you how they play out. So I've created a couple of notches in our nice blue sponge surface of the road surface here. And if I were to push down on the sponge with load that's affecting it, you're going to notice that at the top, the notch is going to come together, and at the bottom, that notch is going to spread apart. And the difference is, am I remembering my stuff right, Jeff? Compression is what I'm seeing on top, and tension is what I'm witnessing on the bottom?
Correct.
Okay, so those forces are constantly going all the time, no matter what.
Yes, under the dead load of the steel and concrete, yes, there's always some bending in the components as they react to gravity. And then as live loads are put on, then those loads change, become bigger in some parts, smaller in other parts.
Okay, and no matter what kind of bridge you have, those forces are still going to act upon it. So let's go to a different kind of bridge. Let's assume for a moment that we're going to talk about an arch bridge. So I've got a nice little piece of cardboard here. If I were to make this into an arch, I'm going to assume if it's just standing like this, Randy, it's not going to be very sturdy whatsoever, correct?
Correct.
So we need to have something else that helps that arch bridge stay up. We've got some great video to show you of the Eads Bridge in St. Louis, the first historic bridge that went across the Mississippi River, which shows you an example actually of an arch bridge. Those arches made with trusses. And if I decide to take this arch that I have cardboard, made of cardboard here, and put it in between the books, these books represent what are called abutments. And that's another word that's important for everybody to understand. Talk about what an abutment is, Randy.
That's what anchors your bridge down. As in all the forces from the loading as it goes to the top here, all those are transmitted down to the outside edges here. And so all that load has to be accounted for in the foundation of your bridge to lock it into place there. So all the loads from the top, traffic and dead loads, are all transmitted down to those abutments.
So if I decide to put a lot of pressure on the bridge now, the abutments help it stay in place. But it's still going to be able to move, right? In the same way we talked about before, the surface is still going to do that bending that it needs to do.
Yes.
Now, we see trusses there in the Eads Bridge.
A truss is a great structural system because it's made up of triangles, different configurations, but the thing trusses all have in common is triangles, and triangles are very stiff. You can put three elements together, pin them at their corners, and they won't move. They'll compress and extend in tension, but they won't move side to side. So you kind of build trusses with these systems of triangles, and it makes the system very, very stiff and very able to carry a lot of load without a lot of material.
And you saw trusses underneath the Eads Bridge, but as we show you this video of the Martin Luther King Bridge, which is another one that spans across the Mississippi River service, you'll see those trusses above the bridge. And you'll notice those triangles that Jeff was just referring to, creating that strength and that support for it. And you see truss bridges in all sorts of forms. Sometimes the truss is above the bridge, sometimes the truss is below the bridge, right?
Correct.
And does it matter at all if it's above or below? Is that just kind of like a aesthetic consideration, or do you have to think other things into consideration if it's above or below it?
Well, part of that is clearance to the river. All right, so if we put our truss below it, then we've got to build the top of the road even higher. Part of it is the length and other things that are consideration. If you want to build, how you want to build it. You want to build it off the river, or you want to build it from up above.
Okay.
So.
All right, good. So we've talked about beam bridges, we've talked about arch bridges. Let's talk a little bit about suspension bridges, which you're probably familiar with. We've got a wonderful image here of the Golden Gate Bridge we can bring you, perhaps the most famous example of a suspension bridge. So you'll notice that the Golden Gate Bridge has a couple of big towers there, and you see all of those cables that are swaying in between the towers. Here we've got a couple of towers, and my string is representing that cable. Now, even if I pull these guys taut, if I begin to put force down on this, life is not going to be good.
Yes.
So what do I need to do, Jeff, to make sure that doesn't happen as I'm crossing San Francisco Bay?
Well, there's a couple things. If you notice on the Golden Gate Bridge, the cables go up and over the towers. So instead of pulling in, that force in the cable is transferred over tops of the towers and then down to really huge abutments, blocks that are anchored beneath ground.
So if I took this string then and made this another one, and we created some abutments over here where that string comes down, and some abutments over here where this string comes down, then you're telling me these abutments is what gives it the strength to work and operate effectively. Mm-hmm. And why do I choose a suspension bridge? Like, is it done because of the location? Like, is it better for longer places or shorter spans, or does that matter? Suspension
bridge is typically used for the longest spans, where you have it's hard to get piers into the ground or beneath the water like you would in the San Francisco Bay. So you minimize the number of piers and you can span a greater distance. And if you notice from the Golden Gate photos, really what you have is you have a hanger coming down from that cable. So really you have a little mini beam bridge between each of those hangers.
Oh, very cool.
So it's not the deck isn't spanning between each of those towers. It's really spanning between each of those hangers from the cable itself.
So the hangers are coming down, and here's my surface down here.
Right.
That's right. So the table, in essence, is representing the surface here, while these represent this. Now, there's a couple of other forces at work that I want folks to understand, and one of those is known as shear. And a shear force is that goes parallel to it or perpendicular to the surface. Remind me, what is shear force?
Perpendicular to the surface. All right, and it'll tend to kind of distort all the shapes. I don't know if this will show up. But as we talked about bending or things like this. Shear is a force across the surface.
So let me go that again. I'll do this. So shear's going down this way. So like if I'm hanging something on my wall, like if I'm hanging a picture on my wall and I pound that thing into my wall, that image, that picture, and the nail or whatever is acting as a shear force against my wall. Is that right?
Yeah.
Okay. Now, if shear does bad things to me, we can also end up with something, because you twisted this around, we can end up with something called torsion, correct?
Right.
And of course, in case you haven't ever seen the video of perhaps the most famous example of torsion, the Galloping Gertie Bridge up near Tacoma, Washington. If you look that one up on the web, you'll find some great video of that. But talk a little bit what torsion does and why I don't want it to happen.
Well, torsion is a twisting, as you indicated there, and torsion does some funny things because it's a combination of tension and compression on different sides. It's a little bit like bending in that way. We talk about bending as compression on top and tension on the bottom. Torsion puts tension around the outside and compression around the inside, since it's often concentrated at a point along the edge, you can get some concentrations that are hard to characterize and may result in some bad things.
And that would not be good. We don't want bad things by any stretch of the imagination. Don't forget, you can send us your questions to live@hectv.org. That's live@hectv.org. We're going to go to our student groups in just a minute for some questions about these forces, and as we do that, we'd also welcome your email questions into the program. But we obviously want to talk about just not these kinds of bridges, beam bridges, arch bridges, truss bridges, suspension bridges. We want to talk about cable stay bridges. So we're going to do a little experiment with you, which gives you some idea of how cable stay bridges work. So we'll ask a couple of folks to come down for us so we can move this table out of the way, and as we do that, we're going to show you a picture of our beautiful cable-stayed Mississippi River Bridge going across the surface of the Mississippi River here. And give us some factual details, Randy, just about the bridge. It's 1,500 feet across.
Yes, because the barge traffic coming down the river there needs a wide angle to swing out wide, and so it was determined 1,500 feet would be safe passage for the boat traffic with the Coast Guard. And so the bridge towers are 400 feet tall as a function of that, and that's 2/3 the height of the St. Louis Arch.
Now you may wonder, you're looking at yourselves right now and you're thinking, oh, so we're going to do a double Dutch experience right here with Randy, Jeff, and Tim, utilizing this nice little string as jump rope. We're going to give you the idea a little bit about how tension and compression work in a cable-stayed bridge, and we've invited our student groups who are joining us interactively to do this with us at the same moment in time. So if you guys are doing it, then you are going to become the tower of the cable stay bridge. And your arms here are going to become the road surface. And the gentlemen, thank you very much, my kind and wonderful assistants, Randy and Jeff, are going to be able to place the cable stay on me in the way it would work. So we're going to raise it up above my head.
Now let's try. Wait, can we do something first here, Tim?
Sure. You tell me what we need to do.
Let's try to push down on your arms. Can you hold me up?
Whoa.
All right.
He was waiting to do that. I just want you to know that. So he's referring there to that live load force that would have been going across me if I was the bridge and trucks were going by. And now we're going to use a cable stay here. They're going to attach it into my elbows. And as you guys are doing this, begin to feel how that makes a difference for your ability to hold up your arms. That indeed, while the rope is on your head, above the tower, so to speak, resting on the tower, it becomes a little easier, at least it does for me, to hold my arms up, to keep them up. Because in essence, the towers are taking a bit of the load. And you'll notice that as Jeff pushes down on me. Now let's, of course, he may want to push down really, really hard to make my life as difficult as possible, but let's see what happens now if we add another cable stay. So gentlemen, pull it out of my pocket there. Thank you, man. We pull that out of my pocket, wrap it out of my hat. And in this instance, we're going to tie it a little further on my body, down to my wrists, so it's acting as one more cable stay that's connecting to the deck surface. And again, you will notice as you're doing this that the compression and the tension forces changes for you a little bit. And you can see as I begin to hold my arms out that it's actually pretty easy for me. And because I know he wants to, and as Jeff begins to push down on me, you're going to see that it's, hopefully even easier. And as we added more and more cables to the process, it would become simpler and simpler the whole way through. So if you're doing this activity on your own and when we come to you guys for student questions, then feel free to let us know what it was like. Did you notice the tension on your head, the compression as you felt down, and what's it like? I feel a little bit like a marionette here as I have these strings all together. But let's go to student questions so we can find out what you guys want to ask about forces at work on a bridge, and we'll weave in some email questions too. Let's go to Maryland first. La Plata, Maryland, what would you like to know right now?
You guys talked about how no matter what, the forces on a bridge are going to cause the bridge to be moving. So I was wondering what the constraints are that engineers use that still consider that movement to be safe in a bridge. Like, what's the maximum amount of movement that's allowed?
Jeff, Randy, who wants to speak to that?
One of the things on the bridge just naturally as it heats up, it expands and contracts. And a very long span like that, as it expands and contracts, there's something called bearings or something, a sliding surface. So those large girders are slide back and forth. And so there's a certain amount of movement there, but you don't want it to go side to side, so it's locked into place so it can't move like during an earthquake. We have a high seismic design in this area here. And the thing, we want it to move back and forth during natural temperature cycles, but we don't want it to move very violently during an earthquake. So there's something called a lockup device, like a big shock absorber type of installation that goes between the towers and girders, so during an earthquake it locks up and the whole bridge swings as once. So there you want it to swing as one big unit, but you don't want the individual pieces coming back into it. But during normal expansion, contraction, and as we constructed the bridge, when you set a section of cables on one side and loaded that up, the whole towers would move maybe 18 inches out of plumb and back and forth. And so those are normal construction loads that we account for, but we do not, you don't want it too excess where you cause damage.
Very cool. Thanks for that question, La Plata. We'll be coming back to you guys for more questions. I want to go up and see if our student groups have joined us from Plum City, Wisconsin. Plum City, if you guys are there, do you have a question right now? Come in and say hello and ask it.
Sure we do. I have one from Dane.
How do you make, the bridges going up?
I think he's talking about near us. We're kind of closer to Minneapolis. There is a lift bridge. They're wondering about that.
Oh, that's a cool question. Jeff, Randy, who wants to speak to that?
That is a cool question. In certain areas, particularly in cities and lowland areas where you need a lot of clearance over the bridge or under the bridge for boats or other things to go underneath, but you don't want to have to put your roadway up that far. I'm getting very animated here. So in that case, if there's not a lot of traffic and you can accommodate a lift bridge or a bascule bridge, where it will actually open up. Some of them open up like a seesaw, others swing to the side. And those are really complicated bridges because typically we talked about bridges moving, but the movements that bridge engineers typically like to see are on the order of a few inches, like Randy mentioned. These things move 30 feet in the air. So there's a combination of a lot of different things. We talked about live load, so the bridge has to move and it's in a different configuration. So there's a lot of things you have to take into consideration when designing a bridge like that.
Thanks for the question, Wisconsin. We'll be coming back to you guys for more questions, so don't hesitate to come up with what they are. I want to weave in one email question as we move on to the next segment of the program. And this comes to us from a viewer wanting to know if one or two of the cables fail, is there like fail-safe stuff? Like if something were to happen to a cable inside the bridge, so to speak, is it prepared that it's okay if one or two go because the rest will make up for it?
Yes, there is a lot of redundancy built into it. The individual cables that go inside one of these sleeves is there between 31 and 73 of these individual cables. And if we have extra cables in there for that redundancy and an entire whole set of cables, if that suddenly disappeared overnight, the bridge will still stand. So there's quite a bit of redundancy built into it, but obviously we want to carefully monitor these over the 100-year design life to make sure you don't ever get to the critical point on that.
Well, let's start talking about this bridge then and the cables. We've got some pieces of equipment we can look at. But first of all, why was it decided that a cable-stayed bridge would go here? I mean, we've got an image that we can show of the Eads Bridge that comes up, and we notice that the Eads Bridge, or those other bridges we saw in St. Louis, basically span the same amount of distance that this new bridge is going to span. So why a cable-stayed bridge this time as opposed to another arch one, for example? Well,
suspension bridge, like you've seen earlier, those can go up over a mile span, but they're the most expensive. Trusses can go smaller, such as the Eads Bridge has a 500-foot span. It so happens we have a bend in the river at this point, and where the barges really have to swing wide. So the Coast Guard said for safety considerations for barge traffic, they want a 1,500-foot. That was established. So the most economical to structure to span that amount is a cable stay. And just as a kind of a added bonus, it's just a very beautiful structure in its own right.
It is, and we've got an animation of what the construction process was like. Obviously, we're past that now. We're no longer at the construction process. Well, this will give you an idea, though, about how they built the bridge from the outside in, and we'll see that happening. And you were always working toward the middle until eventually there would have been some space, some gap in the middle that you had to fill. And we'll be able to see later what the process was like for that to happen. But let's begin to look at some of these pieces of equipment that as we see the cable-stay bridge come together, we know what's actually inside those nice big white pipes that we see. So what you're currently holding in your hand are the actual cables themselves, right?
Yes. What people see when they see the structure is this is protective stay pipe that protects the cables inside. And the cables have a few layers of protection. There's a king wire that goes through, and it's actually 7 individual wires that's twisted together, about the diameter of a penny, as you see here. And then these are greased inside, and a sheathing put over that to also give it 2 other extra layers of protection from rusting. And there's a clamp that goes there, clamped off at the bottom, pulled tight from the top into a proper tension. This little clamp device that fits over the top of there, once it pulls, try to pull it through a small circle there. The tighter you pull, the more tension it puts on there and locks it firmly into place then.
Oh, so we've got that tension going on with the cables themselves to make sure they stay in place once they're put in place.
All the cables have a specific tension, and so make sure all the cables in the sleeve have the same tension amount on those, and each set has a different. It's a pretty complicated process, and from our design firm that how that all comes about, but it's very methodical as we go through in the construction stage. But these are the actual cables that hold up the bridge. We have about 3 million feet of cable in the entire bridge structure.
And you guys are going to have a chance to hear from Tom Tabanero, who also worked on the bridge, and just explain to you the process of putting these cables together. Jeff, let us know, what was Tom's job on the bridge? What did he get to do?
He was the project manager for the contractor. So he was in charge. As a designer, we develop plans, how it should be put together. Then he decides how it actually gets built.
So you've seen the cable. You've seen the pipe that the cable is going to go inside, and now you wonder, so how does all that get connected to the bridge surface to make sure it works properly? Well, let's find out from Tom how they did it.
Well, everything's based on the geometry. So we have 5 different surveys throughout the cycle of building one 40-foot section of deck on each side, so it's balanced. There's 5 different surveys, and depending on the conditions and what the survey results are, we'll adjust the cables to where the deck is in the proper location before we lock it in. This is lifting one of the stay pipes up. This is probably a 600-foot long piece of pipe. Weighs a few thousand pounds, and so you can see the rigging that is attached to the crane hook on the left side of the image, and then on the right you don't see it, but our tower crane has the other end of the pipe. In this photo, this is just after the pipe has been raised. The worker, he's signaling the crane right now, and what they're going to do is they're going to transfer the weight of the pipe from the rigging that the crane's holding on to it. They're going to secure it with, you can see the come-alongs, the orange block and the chain, and so that'll be used to secure the pipe, and then the strand is fed into the tower through the holes that you see. Basically, this is just lifting it in place, and it's interesting to note too is the first strand that we put in, we know what length it needs to be in order to with the pipe sagged in order to be able to get the first strand in. So, you know, there's quite a bit of sag as you're putting that first strand in, and so that strand is actually could be up to 60 feet longer than a second strand or the other strands that are put in the pipe. They're taking this first strand and putting it down. You can see down the gray pipe that goes to the left. Now they're feeding that down and putting it in a particular location in the anchor head. And so that's a process. The blue wheel that you see, we have the strand is set up to the right of the workers you see in that picture. So those strands will actually come off of a reel, a spool, and go up and over the blue wheel and up into the pipe. Once the strand goes through the proper hole in the wedge recess, then now what he's actually doing is he's taking one of these wedges and he's tapping that into the recess to make sure that it's secure. Once the strand gets up to the top, it's in the proper location up in the tower, so then they have a cutting table that you see here. They're securing the strand, and they're going to cut the strand, see, because it's on a reel that's 8,800 feet long. And so they cut that to the proper length, and once they do that, then they feed those strand tails down into the anchorage. So this is within the tower. So the towers are 8 feet wide by 18 feet, and so it's like you're in a big room up in the tower, and you can see the anchors. Now you see the gray piece is part of the cable anchor, the piece that has all the holes in it. That's where the wedge recesses are that hold the cable. And so this would be after we've installed, what is that, 10 or 12 strands, and you can see how they're numbered, and that's where they're parallel. So we make sure to put, you know, the position 5 on that photo, well, that's a mirror image of what's on the bottom in position 5. As you're putting cables in, well, the subsequent cables relax the ones you have in. So you might start out stressing a cable to 25,000 pounds, and when you get done putting the last strand in, the cables might be at 17,000 pounds. So we have a computer system up in the tower so each strand is installed to a different force, and that's for so the goal is when you get all the strands together in the stay that they're at the same force. You pull the wire through to the proper location of the tower, put the wedge in, and then push the strand through the anchor head on the bottom that you see here, and then once you do that, then all the stressing is within the tower.
Tom is actually now working on a project in the New York metropolitan area. Was he able to come back for the opening ceremonies, gentlemen?
Yes, he was.
Oh, very cool. So, but that was an extraordinarily clear demonstration with some great images that the contractors and MoDOT and all the good folks working on this bridge provided to us, so you could see how the process worked to put the cables on the bridge and hopefully make it all work successfully, which it's doing quite nicely right now as we sit here. Let's ask what you want to know, however. Let's go back to our student groups to find out if you've got more questions about anything we've talked about so far, the nature of putting this bridge together, the cables, etc. La Plata will go to you, then we'll go to Plum City. We'll go back and forth as needed. Marilyn, what would you like to know?
When you guys build a bridge, you take into account if a ship was to accidentally hit the top, hit the bottom of the bridge and wedge it upward, you take that into account when you're building the structurally soundness of the bridge.
So in terms of what do you take into account, whether it's hitting the top of the tower, whether it's barges coming through traffic, those kinds of things? How do you take those kinds of things into account?
A barge collision is actually part of the design process. We talked about those live loads earlier. That would be a live load. So we consider the probability of a fully loaded barge impacting one of the towers full on, and those forces are then accounted for in the strength of the materials. As far as something hitting the top of the towers, we don't have anything specifically for an impact to the top of the tower, but we do consider wind on the entire tower itself. And if you were to add up 50 to 75 pounds a square foot on the entire face of that tower, you're probably at 500,000 pounds of force pushing on that tower from wind alone as well.
Wow.
So,
wow. Who'da thunk, so to speak. La Plata, I'll go back to you guys. Another question from you?
Is there anyone, as it said in the video before, is there someone staying in that tower at all times watching the cable pressures?
We actually can bring up a still image of inside the tower. No one's up there all the time, but you can actually climb up inside the tower. Is that right? So you can adjust and repair or whatever you need to do?
Yes, the towers are actually hollow, and that was by design, so you got to have a way to install the cables during the construction phase, but also allows us the opportunity to go up there and do our annual inspections or more needed inspections if required. The one thing nice about this type of system is not one big cable, it's individual cables. So the 100-year design life, odds are you're going to have a few cables that are not going to make it 100 years. So we actually have the capability to swap out these cables under traffic, and in theory we could take out every single cable one by one and replace it and tension it and never take it off traffic. So we do have an annual very regimented inspection process on the bridge, and also one of the telltale signs is the geometry will start to meander a little bit if there's something's going askew there. But and one of the other unique things that we've never designed for at a bridge in Missouri is a security threat assessment. You got the normal seismic things like that we designed for. We actually went through a security clearance to learn about what things we could do to for terrorism, either accidental or intentional damage from explosions, things of that nature.
Very cool. Thanks for those questions, La Plata. Let's go back to Plum City, Wisconsin. We'll do a couple from Plum City now. Go right ahead.
What determines when it's time to rebuild a bridge?
Oh, that's a super question. Thank you for that. What are the things you take into account?
We have annual inspections, and so you do a rating on the bridge and what conditions of the very aspects. And so this bridge is designed for a 100-year design life. That doesn't mean 100 years that it automatically you take it out of service. With proper maintenance, can go much beyond that. So especially if you had a seismic event or something like that, you would do a full-on inspection and definitely look at certain critical items on the structure itself. But every year there was a full-blown inspection. There's actually a traveler system, a little thing that goes on the underneath side of the bridge deck that goes from end to end, where workers can get an up-close look that you can go and get a very close inspection of the girders and things of that portion. And of course the towers are hollow inside, so you can get a good look there as well.
Very cool. Plum City, back to you guys. Another question?
We have several train bridges around us also. They seem so small. The kids were wondering how they can carry the weight of a train.
Oh, cool question. We have a bunch of train bridges that also go across the Mississippi River here as well. Talk a little bit about that.
That is a great question. For one thing, as far as their size is concerned, trains are restricted to tracks. On a roadway bridge, you've got 12-foot lanes for cars, so there's cars, trucks, people may be weaving in and out. On a train bridge, they're restricted to the tracks, so you know exactly how wide that's going to be. As far as the thickness or depth of the girders or other members, what you'll see a lot of times if you look closely is you'll have a lot of girders in a small amount of area. On a roadway bridge, you may have girders spaced at 8 to 12 feet. On a railroad bridge, they may be spaced within 2 or 3 feet of each other. So although it doesn't look as big, there's an equivalent or even more amount of beams or structural components on those train bridges.
Cool questions. We'll come back to you guys again for questions. I want to weave in a couple of email questions now. One tells about how do you plan for the amount of traffic? Like I've heard on the news media that they're planning that eventually this might handle 40,000 cars a day. I mean, how are those estimates arrived at, and how do you guys then figure out live load amounts? Like, does it worry to you like, oh, it's 40,000 vehicles and 20,000 of them are 2-ton trucks or whatever? How does that process work?
Well, I'll take the first part of that. The 40,000, we do traffic modeling and look at all the different access points and what we think the traffic that'll ultimately configure on there. And that won't put it to capacity. We don't think we'll hit capacity until probably about 15 years. And the bridge has 2 full lanes with wide shoulders, and we can actually restripe it to 3 12-foot lanes at that time. But that's kind of a complex thing as far as trying to anticipate, what normal movements, looking at what people take certain ramps from the existing bridges, and we know this is a brand new bridge and will be taking I-70 off the existing Poplar Street, so we know pretty much what traffic goes through there and get a good estimate. The wild card is you don't know. Once people discover a new avenue into downtown, we think it'll be a little more used than that, but it'll take a while for traffic patterns to fully develop.
And when you think about that amount of traffic, is there some sort of basic statistical line like every car is automatically a ton, or how does that work as you calculate?
There are codes, there are requirements that we have to follow, and briefly, we'll consider a full lane of cars loaded up in every lane, and then a truck every so often. The trucks that we design for weigh 72,000 pounds, so we'll put those in our models. We'll move those across the bridge and see how everything's reacting to those vehicles. And we talked about live load and dead load. One of the things we do in design is we have a pretty good idea of what the dead loads are. We know how much concrete weighs, how much steel weighs, but we put a factor of safety on that. So if we say it actually weighs 1,000 pounds, well, let's assume it weighs 1,200 pounds when we figure out what we need to do. For live loads, We don't know if someone's out there with a truck that's heavier than it should be. Maybe 6 trucks happen to be following each other really close. So we put a larger factor of safety. We scale those numbers up from what they should be when we consider what the loadings on the bridge are.
Very good. Thanks for those questions. We'll weave all your questions in again in a bit, but let's talk about now. The towers are built, the cables are there, but you also know as the cables get connected, they have to be connecting to a surface. So let's talk about how that deck surface works. We'll bring up an image first of all, which shows you a schematic of the deck. So you see the different levels of the deck surface that are part of the schematic as you go around here. And you've got girders, as well as the road surface, as well as the top that's called the driving surface. So those things together are going to make up what is the deck surface of the bridge that becomes all the different elements. And you see them here. You see the floor beam, the deck panels, and then of course the driving surface. So let's break that down. The floor beams are those steel girders, and we'll talk about them a little bit more when we talk about how the final bridge came together. But let's talk about the deck panels first and how those deck panels get constructed. And we've got some nice video we can run for you as the gentleman described this process. Guys, where were these deck panels constructed, and how do you go about doing it?
Well, the deck panels, they're precast, meaning cast ahead of time, and that I think was done in O'Fallon out west of St. Louis and then shipped to site. And there's 2 advantages to that. One, it helps speed things up because you can do all this stuff ahead of time and then bring out just what you need. 2, you get better quality control because it's in a controlled environment. You don't have to be out in this 10-degree weather that we have here when you're trying to create these things. So you get a little product that's better quality control and is actually faster for the bridge. So you kind of get, usually if it's one or the other, good quality or faster, but here we can actually get both components with that.
We saw as the panels were being put together, we saw the rebar that was in it. We saw the concrete pour. As they pour the concrete, do they have to think in terms of temperature? I mean, are you pouring I realize you may be pouring the concrete on a 45-degree day. How do weather conditions affect, and do you make any kind of adjustments for what the concrete is supposed to be like in terms of its consistency or whatever the case may be?
We have a full quality assurance on all our materials that go into the bridge. Not only is the concrete tested, but just the different components that go into it. The cement, the rock, there's certain criteria that we have specified that goes into our bridge components, and especially on like a bridge deck panel. Certain temperature requirements that they can't blow because of concrete, freezing, and it will not attain the strength that we desire. But as Jeff mentioned, you can do it. One of the great aspects about doing a precast is you're working on the ground, so you don't have some of the things to contend with. And one of the big things is safety. When you're building it on site, you're way above the river, and certain safety aspects come into play as well.
So the deck panels have been built off-site, and St. Peter's, O'Fallon, Missouri is probably about a 30-minute drive, I guess, from there to where the bridge is actually located. And then, of course, you've got to put those deck panels onto the surface. And so the video we'll run now will show you that process at work as they describe what goes on. So how do you then take the deck panels, they've arrived, and now you're going to place them on the deck surface? What's that process like?
Well, the deck panels, as you see there, it's called cantilever construction. You'll set one section of steel about 40 feet and toward the span out, and so then we'll put the cables on, and then we'll set these panels. These panels are very large. Just a section of steel there, 40 feet, doesn't sound like a whole lot. That's 225,000 pounds, and 6 panels will cover that surface there. Each of those panels weighs 70,000 pounds each. So very large crane makes it look easy, but 70,000, so you got a little over 600,000 pounds. So that's when I'm talking about the bridge tower. Well, actually, you want to move a little bit that direction. And so therefore, then the next section goes on the opposite side of the tower to equalize out that loading, so you're never one out of balance. And you'll see there's also openings in the bridge deck panels where we slide a big bar that's got a threaded just like you would a bolt, and these are kind of like bolted or tensioned together, and that helps overcome some of the loading. And then the gap in between panels, there's a concrete placed in between those sections there to lock it all into place.
So when you actually lock it into place, you do something to affect the tension of the decks so they connect together at the tension you want them to.
Yes. Go ahead, Jeff.
Yeah, I don't know if you noticed, Tim, but when we did the cable stay experiment, those ropes pulling up, they're also pulling in. Okay, so there's a force inward on your arms, which tends to, towards the middle, it tends to want to pull things apart. So that the post-tensioning, putting those steel rods in after, helps lock that in, make sure we don't get any cracking. As Randy mentioned earlier, concrete is weak in tension, it wants to break. So that the post-tensioning or pushing together with those rods helps prevent that.
Now the bolt that I have here, is that the kind of bolt you're talking about, or is this being used in the girders to connect them? Or
sorry.
That's a bolt just to hold of the girders, but it basically is something that's much longer than that. It's just a bolt that's maybe 40, 50 feet long, and it's threaded on the end, so when you tighten those group of 3 panels together, that locks them and puts that tension in that group of panels, and then the next section will be done the same thing.
So this is the kind of bolt that goes down into the girder as you're connecting the girders together. Let's talk about putting the last girder in place. We've got some great video of the last girder going into place here as we describe this. And give us an idea, because obviously you're building the bridge out to the middle, the temperature's doing something, all sorts of things are happening. Maybe you think that last girder needs to be 10 feet, and all of a sudden you have to do calculations, I assume, to figure out what it needs to be, right?
They did. The contractor took a lot of surveying measurements throughout the day as temperatures varied to see exactly how long that piece would be. And actually it wasn't completely fabricated. It was ready, but it wasn't completely fabricated until a few days before, when they knew about what the temperature would be on that day that they set it, and how large that gap may be.
So we see in this video the girder coming in, flying down. This is a ceremonial moment in time where the bridge actually gets connected, and then you've got to obviously put the deck panels on it as well. So I could never imagine being one of the people who's going to like lean out there and put that into place. That would never be a job for me. But this is a process that took basically an entire day, or a little bit longer than that. Talk a little bit just about the nature of making sure it all works successfully.
Well, it did take a lot of, not just that particular day, many weeks of planning, constant surveys, morning and afternoon adjustments. As mentioned, we cut that final piece to order. Some fine-tuning of the cables, because when you adjust the cables, the deck goes up or down, and also side to side. So we had numerous meetings and a lot of planning to go into the effect, and luckily we had very good temperatures in July. It was temperatures get to be very warm in St. Louis. Not uncommon to get up close to 100, but that particular day was in the 70s, 60, some would have been ideal. So we're about perfect for the temperature, and because you got to have it perfectly match up so the bolt fits right into place for those final sections.
And of course the bridge does indeed get completed together, and you're actually able to drive across it now. And that means if you're going to drive across it, it's not just that the bridge has to come together in the middle. Obviously you have to have access ramps that get up to the bridge. So we've got some video that we want to show you about that, and some images, because I think it's just kind of fascinating when you think about how all these different highways come together. So let's go to an image which shows you the map aerial view of all of these connections that come together. It might not make sense to you geographically if you're not in the St. Louis area, but don't worry about that. You see a bunch of red, you see a bunch of yellow. All of this is just all sorts of different roads. This is downtown St. Louis. Obviously, Illinois is on what would be the east side of this image. Downtown St. Louis is on the west side of the image. And you've got all these things that they've got to connect. That process alone is time-consuming and obviously a significant amount of the project. But what you end up with then are the following things. And we've got a couple of split-screen videos that we can show you. On one side, you'll see actually driving across. On the other side, you'll see the animation of accessing. And one way you can access the bridge is from I-70. You're traveling east on I-70 going toward downtown St. Louis. And just before you would get to downtown St. Louis, you're actually able to curve across and access the bridge instead. Gentlemen, talk a little bit about the process of just connecting the road together to everything that was there.
Well, a lot of people think of the signature bridge that you see, but there was actually 37 individual projects that make up the entire corridor. You got to connect the bridge to the existing roadway. It connects to I-70. It's meant to be a through connection for I-70 in the St. Louis area, and it does connect into I-70 on the St. Louis side. However, to get access from other roadways on the Illinois side, it also connects in from I-55 and I-64 as well as I-70. So a lot of infrastructure had to go into place to make sure all the ramps and the tie-ins and everything. So the entire corridor was about a $695 million investment between the both states. But the one piece that most people recognize and remember when they drive across is the signature piece, which is the main span bridge.
And that's what you're seeing there in those videos. That main span as you drive across it, exceptionally impressive. When I had the opportunity to drive across it on Sunday after it opened officially, very impressive as you drive across it, and you're kind of like locked into looking up, even though of course you know you're supposed to be driving forward just because the towers look so cool. Let's find out what more questions you guys have about deck surface, about the road, connecting roads, or anything about bridges. I'll weave email questions in a bit. But let's go back to Maryland. La Plata, a question from you.
When you guys talk about the cables, how do you test to make sure one cable isn't like weaker than the rest? and in the installation and making the bridge and any of the cables break?
Very cool question. So testing the cable, and did you have any breakage problems as you were putting them in?
No, the testing begins actually before we install the cables. They're a very regimented process to the steel properties, and actually we put it in a giant machine that pulls the cable and relaxes it 2 million times in very rapid order, and that simulates about 20 years, so you don't have an overall extension or elongation of your cables over time. And so that is pre-tested to make sure, and the quality control actually during the manufacturing process, but on site to make sure we have the proper tension as we test each individual cable as it goes in. After one set of cables is done, we'll go back and check individual select cables at random, and to make sure they're all within 5% of each other, that make sure nothing happened in the meantime during the course of that. So that's part of our quality control, quality assurance process that went on throughout the construction of the bridge deck.
Thank you very much. Let's go back to Wisconsin. Plum City, a question from you.
How many bridges have cables that have broken?
That may be a number we can't give you, but because he asked how many bridges have cables that are broken, but is that a likely occurrence at all?
The cable stays are relatively new, so really, you know, you wouldn't anticipate anything for toward the very end. So there's the various monitoring processes that you go to make sure, and so that's the reason you do have quite a bit of redundancy built into her, just to take out any doubts. So, and even if you have several cables break, that doesn't mean your bridge is going to fail or fall in or anything like that. That just means that you'll have to go and replace those cables, and you'll see maybe some geometry changes in your deck or something like that. So it's not something we call fracture critical, that if one cable, you know, your whole bridge falls down. So I'm not aware of any issues that we had in anywhere in the United States or across the world where you had a problem with cable breakages. The common enemy of steel is rust, and so therefore that's the reason we have the many layers of protection there, and constantly monitor that to make sure we don't have any of those type issues.
Thanks for that question, Plum City. You mentioned the constant image of steel is rust. Obviously, that's based on weather, and we've got a question that's come to us from Roger in Troy. Thanks very much, Roger. Asking, how does the weather play into effect when you build the bridge? Just in a general sense, how do the environmental conditions of the construction phase play into what you end up having to do?
Well, it's a constant fight for the contractor. You know, we build these things outdoors as a matter of course. A bridge like this, the river came into play quite a bit. We had flooding several years ago when the contractor was just trying to work in the water and come up out of the water, so they had to fight that. They had to shut down a few times just based on the river levels. And other times the river was too low, and they couldn't, and their barges sat too low. They couldn't reach what they needed to at the top. You know, Randy talked about the temperatures earlier. You know, concrete placement has to occur when the concrete won't freeze. So you have to make sure things are covered or enclosed. You know, areas are enclosed so that the concrete will stay the temperatures it needs to. And the workers themselves, it's a tough job. Those guys are out in all the elements, working in rain and cold and heat. So you just have to be aware of those things ahead of time and take them into account.
And goodness knows we've had a very cold winter this year, so I can't imagine working in negative 5-degree temperatures. Don't forget, if you don't have a chance to get your question in during the program, just email them to us at live@hectv.org, and we look forward to emailing you responses back. So whether you're joining us via video conference, the web, or television, send those to us at live@hectv.org. Let's talk a little bit about the excitement of opening it up and some other elements aesthetically related to the bridge. We've got some video we can show you here, a little montage of a number of elements of specific parts of the bridge, and talk, if you will, just a little bit about, did you have to change things as you went along? You know, why did you decide to paint it white? Why does it look the way it does? Those kinds of things. Let's find that out.
Well, the bridge is painted white, and that was for a couple reasons. One, when it is lit, it will light up more and more brightly. The other consideration to that is the color is similar to concrete itself. So if anything comes off in the future, you know, it will just blend in a little better. That coverage is really just an aesthetic consideration. It's not a protective coating. So it just helps reflect that light better. Some of the changes that took place during construction, the contractor did some testing of the bedrock and made a change. They wanted to use fewer larger shafts down in the bedrock than the original design. So that saved them some time and money by using those fewer larger shafts. Harder to build, but there were less of them. There was some, I think we added 1 inch of concrete to the median barrier Wouldn't sound like very much, but when you've got 1,500-foot main span plus 600 foot on other spans, figured out it added about 900 pounds of force to each cable. And Randy talked about excess capacity earlier. You know, we don't design things. We talked about factors of safety. We don't design things so that it's just gonna break if under the heaviest possible load.
I want to ask you about the outside of the bridge of the girders, because the median is concrete in the middle, but the edge of the bridge is obviously not a concrete median. It's open, right, as we see in that image. And why was that decision made? Does wind affect that? I mean, is it a good idea that there's actually kind of like the wind going through those open spaces? Would that have mattered?
That was a wind consideration. A structure like this, we actually had scale models built of the bridge and were tested in wind tunnels. And what those models initially told us with concrete bale or railing or a solid railing on the outside is that the bridge wanted to twist a little. We talked about torsion earlier. It wanted to twist a little bit. It wasn't anything that was going to be a problem for force or making the bridge fall down, but it would have been uncomfortable for users of the bridge. So the open rail lets that wind pass over and minimizes that fluttering effect.
As a consumer of the highway, I say thank you for that. It would have been kind of bizarre, even if it wasn't a safety issue, to think you were driving across it. We've got some wonderful footage of the bridge lit at night, and of course it's gorgeous aesthetic addition to the downtown skyline. Talk a little bit about the night lighting and just the nature of the aesthetic appeal of the cable-stayed bridge.
Well, it is inherently really a beautiful type structure. The challenge with the lighting was to light it up enough that you could see it from far away, but not so bright that it's going to hinder traffic on the bridge. And you want to be able to see it from 5 miles away, but not, you know, see it from space. So you had to kind of balance those things. The cables are all lit up from underneath. There's a light that shines up each cable, and I think that shows up pretty well there in that footage. And actually, each of those lights is 1,000 watts, about what it would take to run a microwave. So you've got about 160 microwave ovens on all night long.
And Randy, the bridge just opened over the weekend, and we've got some great footage of the opening ceremonies. Talk a little bit about, oh my gosh, this project that I've been working on so long is over. The excitement of the opening process. You know, whether it was a professional or personal challenge, or really a great thing about being part of this project.
It was just a great event. We invited the public out. Since this will not be a pedestrian bridge, this will be the only opportunity for people to walk and get a close-up look at the bridge. And it is spectacular when you get to see it up close. And we invited the public out for a showing of it, along with some festivities. We had a great turnout. We were estimating, we had a 6K run event in the morning. We had almost 3,000 runners go across. And we anticipate we had probably had about another 12,000 onlookers to come out and enjoy the celebration of the new, the official name is the Stan Musial Veterans Memorial Bridge, to honor the veterans in the area, and also a longtime baseball Cardinal great who was just a great ambassador for the community of Stan Musial. Just a great event, and it was just so wonderful to finally share our big project with the world, and many pictures were taken that day. A lot of smiles on everybody's face, even though it was a very cold day. It was just heartwarming to see all the people that come out to get to share in our project, and
including the Clydesdales.
And including the Clydesdales. That's a tradition on the opening day. The Clydesdales, Stan Musial wrote out until his passing, and so we were honored to have the Musial family go across to the ceremonial crossing with the Budweiser Clydesdales, followed by many different various veterans groups, antique cars. So it was a wonderful celebration and a great way to kick off the opening of the new bridge.
It was a great way to kick it off. I enjoyed walking across it myself on Saturday. It was a little cold, but very, very cool from a good perspective. Just a few minutes left in the program. La Plata, one final quick question from you from Maryland. Go right ahead, La Plata.
In several of the videos, there was snow accumulated on the bridge. Is there a special process in removing the snow on that bridge?
Any special process? That kind of intrigued me, actually, as I drove across it on Sunday and there was snow falling. Is there any kind of different process for removing snow and dealing with it than it would be any other highway construction?
No, but on those deck panels, there's a wearing surface, a 2-inch special latex modified concrete, which is very impermeable, which doesn't absorb, so it kind of keeps all the salt out. But we do have a lot of snowfall in the area, especially this winter, so we had the salt on it and the blades of the trucks going across, pushing snow to the side. It's a little rough on the stripes, but should not hurt our bridge deck. And we go through in the springtime and wash all that salt residue off and make sure it's clean, so we don't have it sitting there all summer and for the corrosion purposes.
Great. Plum City, your final question?
How long does it take to build a bridge start from full?
How long does it take?
Yeah.
We had about a year and a half in the design process, but from the very beginning when we actually started construction, it was a little under 4 years for this particular bridge. So depends on the size and complexity of the bridge. And as Jeff mentioned, we had a lot of flooding. We had days added onto the contract. It was originally going to, so each day it flooded where the contractor couldn't work, you got an additional day. So we had many of those days built into the contract as well. But even with that, we were under 4 years construction time. And the contractor worked, especially during the foundation stage, worked 2 10-hour shifts Monday through Friday and 2 8-hour shifts every Saturday. So it was a very aggressive schedule and something a lot of hours and time went into.
Very cool. Jeff, Randy, thank you so very, very much for being with us for this program. This is the second in our series dealing with the building of the Mississippi River Bridge. We got the chance to interact with Jeff and Randy and Tom last year as well. Part 1 was all about building the bridge foundations and what that was like. So you can actually see that archive on our website as well as the archive of this program, which will be up and running next week as well. And together you get an idea about how the bridge was put there from the ground up, so to speak, and then eventually from the towers down. Gentlemen, thank you both very, very much. We want to end today's program with you getting a chance to see this process from beginning to end. Don't forget, you can always email us your questions to live@hectv.org. This program will be archived on our website in just about a week. And if you want to use it as a program in your classroom later, then send us your email questions at that time and we'll happily send you answers as you deal with the archives as well. But let's end the program with the bridge being built from beginning to end. Thanks, everybody.